Now that we've learned how to do proofs both directly and indirectly in Chapter 4, we're going to focus on our last new type of proof in this course, which is proving formulas through mathematical induction. So this is one of the most useful and probably the simplest proof techniques that is available in both combinatorial mathematics and computer science. So once proven by mathematical induction, its theorem is known just as certainly as if it were proven by any other mathematical method. To use mathematical induction to explore conjecture, you ask yourself, is there something about the form of the pattern in one term that ensures the pattern will be true in the next term? If so, this implies that the pattern holds for every subsequent term. So how does this work? Our method of proof by induction says we're going to let P of n be a property that is defined for integers n. Then an induction proof requires two steps. The first is your basis step to show that P of a is true for some fixed integer a. And then we have our second step is our induction step. We're going to show that if P of a through P of k is true, then P of k plus 1 must be true. So essentially we're going to be proving a conditional statement over and over and over and over and over again. So the easiest way to picture this process is with dominoes. We're going to pretend that we've set up a row of dominoes and you want to knock down the first one. What happens? Once you tip the first domino, the next one will fall. Then the second domino knocks down the third, the fourth will knock the fifth, etc. And the process continues up through some arbitrary kth domino, which will then in turn knock over the k plus 1th domino. Thus, this is the way of induction. So we will show that if the kth domino falls over, then the k plus 1 domino must fall over. If a sum with a variable number of terms is shown to equal an expression that does not contain either an ellipsis or a summation symbol, we say that the sum is written as a closed form. And the mathematical induction proofs we're going to be proving are going to be ones such that the expanded form is equal to a closed form. So we're not going to be using the summation symbol here. Let's look at an example of how this would work. We want to use mathematical induction to prove theorem 5.2.1, the sum of the first n integers. So here what we know is that for every integer n that is greater than or equal to 1, 1 plus 2 plus 3 plus all of the other integers up through n is equal to the closed form n times n plus 1 all over 2. So we could have written our expanded form on the left as the sum as I goes from 1 to n of I. We just wrote these all out in expanded form. So that is our tie-in to section 5.1. So how would we even go about starting this proof? Well, remember, we're going to let P of n be this property. So let's start there. We're going to say let P of n be the statement here that we were given, 1 plus 2 plus 3 plus all the way up to adding up plus n is equal to n times n plus 1 all over 2 for all n in the set of positive real integers. So what that means is our very first case here, our very first domino, is when n equals 1. So that is where we start our proof with our basis case. Now, don't think that you don't have to write in the P of n step, because you do have to define what P of n is before you can use it in your proof. So everything we're writing is part of our proof here. So when we turn these in for homework on an exam, when we write an induction proof here, we need this statement to say what P of n is before we start using it. So that's part of our proof. And then we're going to start with our base case, or our basis. So our basis case says that we want to show that our very first entry in our summation is true. So we're going to show that P of 1 is true. And what that means is that we need to show that 1, which is our only term on the left-hand side because it goes up to just 1, is equal to 1 times 1 plus 1 over 2. So we would say then P of 1 is, and let's show that, 1 equals, so we did just 1 on the left-hand side as our first term, and now we plug in n equal to 1 here and here, so in our ends. So 1 equals 1 times 1 plus 1 all over 2. And we'll say that 1 times 1 plus 1 over 2 is equal to 1 times 2 over 2, which is 2 over 2, which equals 1. So we would say the left-hand side of P of 1 equals the right-hand side of P of 1. Therefore, P of 1 is true. So we have shown that P of 1 is true. That is our basis case. In terms of our dominoes, that means we've knocked over the first one. So now we're going to assume that if that holds true for P of 2, P of 3, P of 4, P of 5, which we could show if we kept doing this basis case over and over again, if we use the same process, we could show that 1 plus 2 is equal to 2 times 2 plus 1 all over 2. So we could keep adding them up and keep going for each one. But what we want to do is generalize this into saying that if I can show that this holds true up through the arbitrary kth case, then the k plus 1 case is also true. So if I can knock down the first k dominoes, then the k plus 1 domino will also fall. So that's what we're moving into with our induction step. So let me scroll up here so we can write in our induction step. So for our induction, we would say that we want to show that, right? We want to show that for all k in the set of our positive integers, if P of k is true, then P of k plus 1 is also true. This should look strikingly familiar to a universal conditional statement, like all the ones we were proving in chapter 4, because it is. Essentially what's happening is we're proving that this conditional statement holds true for every single value of k. It's kind of a cool process. So here we also know from our experience in chapter 4, that means that we can suppose that k is a positive integer and that P of k is true. Right? That's what we learned from chapter 4 from our universal modus ponens. We're going to lean into the same thing. We're going to suppose that k is a positive integer and that P of k is true. So that's where we're going to start, is we're going to say that suppose k is some positive integer such that P of k is true. Then we can define P of k by saying P of k is. And now we're going to go back to our P of n statement, and anywhere that we have an n, we now will turn it into a k, just like we were using function notation. So we would say 1 plus 2 plus 3 plus our sum all the way up to the kth term is now equal to k times k plus 1 all over 2. This is essentially what we're going to use as our pseudo definition. Because when we try to show that P of k plus 1 must be true because this one is, that it's compelled to be true, just like we did for all of our other conditional statements, we're going to use P of k in our work, in our algebra. So how does that work? Well, let's see. So we need to show, so we were tasked with showing that P of k plus 1 is true. So what does that mean? Then, let's see here, P of k plus 1 is, and that means we're showing that 1 plus 2 plus 3 plus all the way up, our sum all the way to k plus 1 is equal to k plus 1 times k plus 1 plus 1 all over 2. So we must show that this is also true. The way we're going to do this is we're going to work with one side of this equation at a time. So the left-hand side of P of k plus 1, and then the right-hand side of P of k plus 1. So let's do that. Let's start with, and let me scroll up again, and let's start with the left-hand side. So we would say then the left-hand side of P of k plus 1 is, and that's where we have our 1 plus 2 plus 3 plus our sum all the way up through the k plus 1 term. Now here's the thing, working with only this side, I can say without a doubt that I also know that this is the sum from 1 plus 2 plus 3 plus all the way up to k, and then we added one more term, which is k plus 1. And the other thing that I know is that I actually have a definition for 1 plus 2 plus 3 plus all the way up to k, the sum of the first k terms. We define that back here in our P of k. We said equivalently 1 plus 2 plus 3 plus all the way up to k, the sum of the first k terms, is also equal to k times k plus 1 all over 2. So we can then rewrite this expression to k times k plus 1 all over 2, and then add our k plus 1 term. And then when we try to put them both over the same denominator, we still get k and k plus 1 here. It's all going to be divided by 2, but k plus 1 isn't currently divided by 2, so we need to multiply it by 2 over 2, so it's going to have an extra 2 here. So we're going to have a 2 times k plus 1. And again, that's because we would need to multiply, and I'll put this over here, scratch. So k plus 1 would be multiplied by 2 over 2 in order to put it over the same denominator. And then we combine them together. And here's where a little bit of the magic happens. And that magic is brought to us via algebra. Because now we can look at our new simplified expression as k times k plus 1 plus 2 times k plus 1. And both terms have a k plus 1 that is common, and so we can factor the k plus 1 out, and we are left with just k and plus 2, all over 2. And I'm hoping that you recognize that this is what the right-hand side of P of k plus 1 will simplify into, because that's exactly what we're going to show. Because now when we look at that right-hand side, and we have then the right-hand side of P of k plus 1 is, we found up here that it was k plus 1 times k plus 1 plus 1 all over 2. And if we simplify that, we get k plus 1 times k plus 1 plus 1 all over 2, or k plus 1 times k plus 2 all over 2. And much like in our basis case, we now have a left-hand side that equals a right-hand side. So we would say thus, the left-hand side of P of k plus 1 equals the right-hand side of P of k plus 1. Therefore, P of k plus 1 is true. We would say it follows by induction that P of n is true for all n in Z plus. And we finished, so we'll write our QED, or put our box. For example, 5.2.2, we want to use mathematical induction to prove that for every integer n that is greater than or equal to 1, 1 plus 3 plus 5 plus all the way up to adding 2n minus 1 is equal to n squared. We're adding up the odd integers here. So as usual, we want to start by saying let p of n be the statement. And here it would be that 1 plus 3 plus 5 plus all the way up to 2n minus 1 is equal to n squared for all n in z plus. And we won't always have just a set of positive integers. It so happens that on our first two examples, they all start at 1. So then we need to show our basis case. And much like example 5.2.1, this means that we want to show that P of 1 is true. Then P of 1 is, well, it would be just 1 on the left-hand side, and it would equal 1 squared. And 1 squared equals 1. So we would say the left-hand side of P of 1 equals the right-hand side of P of 1. Therefore, P of 1 is true. And our basis step is done, and we can move on to our induction step. So for our induction step, remember that we want to show that for all k in the set of positive integers, if P of k is true, then P of k plus 1 is true. And just as before, we know we can suppose that, right? Suppose that k is a positive integer such that P of k is true. We can assume that much is true. Then we can say P of k is, and now we go back to our P of n statement and we sub back in k anywhere we have an n, just like we were using function notation. So we would have 1 plus 3 plus 5 plus the sum all the way out to now 2k minus 1 is equal now to k squared. And remember, on the next step then, we are going to use this definition, our pseudo definition here, to show that P of k plus 1 is compelled to be true. So our next step is to show that P of k plus 1 is true. Then we have P of k plus 1 is, will be 1 plus 3 plus 5 plus all the way up to, now this is where the fun part comes in, 2 times k plus 1 in parentheses minus 1. And it's going to equal k plus 1 quantity squared. So our hope here is that when we start looking at the algebra involved on the left-hand side, that we can get it to the form of k plus 1 quantity squared. Because if we can, our right-hand side is already k plus 1 quantity squared. So if we can factor it down to k plus 1 times k plus 1 and get k plus 1 quantity squared, all of the hard work is done for us and our proof is finished. So we will say then the left-hand side of P of k plus 1 is, and let's look at it, we get 1 plus 3 plus 5 plus dot 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 plus 2 and k plus 1 minus 1. And we know again, same as last time, that the first k terms are 1 plus 3 plus 5 plus all the way up to 2k minus 1. And then we added on one more term, which is our 2 times k plus 1 minus 1. So once again, just as before, we know that this sum can also be written as k squared. So this one's not even going to have a fraction. The first one had a fraction, this one does not. So this one should be even a little bit quicker here. So we end up here with k squared plus 2 times k plus 1 minus 1. Or k squared plus 2k plus 2 minus 1. Let me scroll up a little here. Or k squared plus 2k plus 1, which happens to be k plus 1 quantity squared. And we already know this is our right-hand side, so actually the hard work is already done. The heavy lifting is finished. We need to say then the right-hand side of p of k plus 1 is also k plus 1 quantity squared. Thus, the left-hand side of p of k plus 1 equals the right-hand side of p of k plus 1. Therefore, p of k plus 1 is true. So we would say it follows by mathematical induction that p of n is true for all n in z plus. And we're finished. Now that we're getting the hang of how this induction thing works, let's see if you can try this one on your own. So I'll get you started, and I would like for you to pause it and try it on your own and see if you come to the same math on this one. And I will say this one's going to have slightly more challenging algebra, but I think you can do it. So let's write our statement first. And it asks us to use mathematical induction to prove that for every integer n that is greater than or equal to 1, so we've got z plus again, 1 squared plus 2 squared plus 3 squared plus all the way up to n squared is equal to n times n plus 1 times 2n plus 1 all over 6. So yeah, this might be a bit more challenging in terms of algebra, but I think we can handle it. So let's start with letting p of n be the statement 1 squared plus 2 squared plus 3 squared plus all the way out to n squared is equal to n times n plus 1 times 2n plus 1 all over 6 for all n in the set of positive integers. Our basis case is going to be the same as the last two. Show that p of 1 is true. Then we know that p of 1 is, well, on the left-hand side, we just get 1 squared. And on the right-hand side, we get 1 times 1 plus 1. Let's see here, times 2 times 1 plus 1 all over 6. And we know that 1 squared equals 1. And 1 times 1 plus 1 times 2 times 1 plus 1 all over 6 equals 1 times 2 times 3 over 6, which is 6 over 6, which is 1. So therefore we have the left-hand side of p of 1 equals the right-hand side of p of 1, and therefore p of 1 is true. So our basis case is shown. And now we get to move into the oh so fun part of the induction with all that algebra. But we can manage. So for our induction step, induction, there we go. We want to, right? We want to show that for all k in the set of positive integers, if p of k is true, then p of k plus 1 is also true. So we are going to suppose that k is in the set of positive integers such that p of k is true. Then we know that p of k is 1 squared plus 2 squared plus 3 squared plus all the way up to k squared. And now it's going to equal k times k plus 1 times 2k plus 1 all over 6. And now remember, this is where in the next part we need to show what p of k plus 1 is then. So we must show that p of k plus 1 is true. So then we know that p of k plus 1 is, and let's write it all in. We end up with 1 squared plus 2 squared plus 3 squared plus all the way up to, instead of k, now we'll have k plus 1 squared. And on our right-hand side of p of n now is p of k plus 1, we end up with k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1, and it's all over 6. So we can see where our algebra is definitely going to get pretty fun here in a moment. So we're going to start once again, right? Then we're going to start here with the left-hand side. The left-hand side of p of k plus 1 is 1 squared plus 2 squared plus 3 squared plus all the way up to k plus 1 squared. And once more, we know that that's the same as the first sum of the first k terms plus the k plus 1 term. So our first k terms are 1 squared plus 2 squared plus 3 squared plus all the way up to k squared. And then we added this k plus 1 term to get to the sum up to k plus 1. And again, just as before, we know that 1 squared all the way up through k squared, the sum of the first k terms, here is the same as k times k plus 1 times 2k plus 1 all over 6. So we end up with, let's see here, that is k times k plus 1 times 2k plus 1 all over 6 plus our k plus 1 squared. And now we learned from the last time that we have a fraction that we're going to have to multiply the k plus 1 squared by 6 over 6 in order to put this all over the same denominator. So we'll end up with k times k plus 1 times 2k plus 1, right? Plus, and now we'll have to include a 6 here in front of our k plus 1 quantity squared, and it's all over 6. So this is where our algebra gets very fun, because we need to factor out what is common. And what is common here is a k plus 1. And once I pull out a k plus 1, I'm left with k times 2k plus 1 and plus a 6 times the leftover k plus 1. And it's all over 6. So we have a k plus 1, and then we get 2k squared plus k plus 6k plus 6, all over 6. So we end up here with 2k squared plus 7k plus 6. So k plus 1, 2k squared plus 7k plus 6. And if you wanted to use the AC method, you would say what multiplies to give me 12 and adds to give me 7, and you would use 3 and 4. And when you do either the AC method or you do the guess and check method, you end up with k plus 2 and 2k plus 3, all over 6. If you want a reminder of the AC method, This is a note off to the side. This is not to be included with your proof. This is just a note from me to you, the AC method for 2k squared plus 7k plus 6. Well, multiplies to give me 12, so 2 times 6. So AC equals 2 times 6, which is 12. And B is 7. So I'm looking for what two numbers multiply to give me 12 and add to give me 7. And I'm using 3 and 4. So we would do 2k squared plus 3k plus 4k plus 6. And now we would factor out just a k here, and we'd get 2k plus 3. Just a 2 here, and we would get 2k plus 3. So we get 2k plus 3 and k plus 2, which is exactly what we found. So if you are struggling to remember how factoring works, you're going to really want to spend some time on a place like Khan Academy to go back and remind yourself how to factor, because we're doing a lot of factoring in this chapter. Hopefully it's review for most of you and you'll feel confident in doing your factoring. If not, the other option is you can multiply all of these binomials out and get really gross looking. This one would be a cubic, but you could do it that way if you really want to. Otherwise, I would just suggest reviewing your factoring a bit. And now that we've got our left-hand side simplified, let's look at our right-hand side. So we'd say the right-hand side of, the right-hand side of P of k plus 1 is, and that's where we got, let's see here, we had k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 all over 6. So it looks kind of gross. But once we start to simplify, we get k plus 1 times k plus 1 plus 1 times 2k plus 2 plus 1. And I hope you're seeing already that this is going to be the same thing. It's going to be k plus 1 times k plus 2 times 2k plus 3 all over 6. So we would say the left-hand side of P of k plus 1 equals the right-hand side of P of k plus 1. So therefore, P of k plus 1 is true. And it follows by mathematical induction. And you could just say induction here. It's two. I think I kind of vacillate between the two. So it follows by mathematical induction that P of n is true for all n in the set of positive integers, and this one is also finished. For example, 5.2.4, we're going to look at a different kind of induction proof. In this case, we have an exponential function. And notice that this one starts with n being greater than or equal to 0. So our basis case this time is going to be P of 0. So here we want to use mathematical induction to prove that for every integer n that is greater than or equal to 0, 1 plus 2 squared plus our sum of all these powers of 2 up to 2 to the n is equal to the expression 2 to the n plus 1 minus 1. So we're going to start this one the same as we've started all of the other ones. We're going to let P of n be the statement. We're going to write out our statement 1 plus 2 squared plus all the way up to 2 to the n is equal to 2 to the n plus 1 minus 1 for all integers n such that n is greater than or equal to 0. So notice we couldn't use z plus this time because remember the set of positive integers begins with 1, not with 0, because remember 0 is neither negative nor positive. So we have to write a slightly more complicated domain here. But our basis case, remember this time now, is going to be to show that P of 0 is true. So then we know that P of 0 is. Well, this is kind of an odd one because on the left-hand side, it's just the first term, again, which is 1. But on the right-hand side, right, it's going to be 2 to the 0 plus 1 minus 1. The other way to think of the left-hand side is you could also say it was 2 to the 0. So it works either way because anything raised to the 0 power is 1, except for 0 to the 0. See, and we also know that 2 to the 0 plus 1 minus 1 is 2 to the 1 minus 1, just 2 minus 1, which equals 1. Thus, the left-hand side of P of 0 equals the right-hand side of P of 0, and therefore P of 0 is true. So not terrible, just a little different from what we were doing before. We'll find that our induction step is very similar to what we were doing, just takes on a slightly different look. So as usual, we want to show that for all k in a set of integers such that k is greater than or equal to 0, if P of k is true, then P of k plus 1 is true. Right? So we're going to suppose that k is an integer such that k is positive, so it's also could be 0, right? So k is an integer such that k is greater than or equal to 0, and P of k is true. And I think in the previous ones we said such that P of k is true. You could do another such that is okay. You could say, suppose that k is an integer such that k is greater than or equal to 0, and such that P of k is true. It's the same idea. You're just trying to find a way to write it that's not as awkward as maybe saying a whole bunch of such that's. We could say, suppose that k is an integer and k is greater than or equal to 0, such that P of k is true, but it still sounds a little awkward, so I left the such that in the domain and just changed the other such that to an and. Do what works best for you here and what just naturally makes sense if you read it aloud. Okay, so we're going to suppose that k is an integer such that k is greater than or equal to 0 and P of k is true. Then we know that P of k is, well, on the left-hand side we would have 1 plus 2 squared plus the sum all the way up to the 2 to the k term. And on the right-hand side we have 2 to the k plus 1 minus 1. And we know we're going to use this later when we start to show that P of k plus 1 is true. And that's our next step. Show that P of k plus 1 is true. Then we have to show them that P of k plus 1 is. And here we would say on the left-hand side we'd have 1 plus 2 squared plus all the way up to 2 to the k plus 1. And it's going to equal 2 to the k plus 1 plus 1 and minus 1. And you're going, where did all these extra plus 1s come from? 2 to the k here, well, 2 to the k plus 1, right? We had a 2 to the n, becomes 2 to the k plus 1. But now when we look at 2 to the n plus 1, and we're replacing n with k plus 1, we're going to have this is now k plus 1 plus another 1. And that's where we get this expression here, k plus 1 plus 1. So now we're going to work with just the left-hand side, and then we're going to work with the right-hand side. So let's see here. So then the left-hand side of P of k plus 1 is, and that is our 1 plus 2 squared plus all the way up to 2 to the k plus 1. And I'm going to scroll a little here so we have room to work. And we know that this is the sum of the first k terms, 1 plus 2 plus 2 squared plus 2 cubed plus 2 to the fourth, all the way up to 2 to the k. And then we added this 2 to the k plus 1 term. And again, we also know that the sum of these first k terms, right, the sum of the first k terms is the same as 2 to the k plus 1 minus 1. So we're going to say this is 2 to the k plus 1 minus 1. And then we're going to add to it a 2 to the k plus 1. And this is where your algebra skills are going to go, hold on a second, let's think about this. So if I have 2 to the k plus 1, and I add another 2 to the k plus 1, I now have 2 to the k plus 1 terms. So if you think about it this way, if I have one red apple, or one here, I'll do one red heart because I'm better at drawing hearts. If I have one red heart minus 1 plus another red heart, then I would have 2 red hearts. Well, that kind of looks like an apple, I suppose, minus 1. And so here, so this is just this is just scratch work. This is to show you how this works. So the way we're going to simplify this next step is that we're going to say then I have 2 to the k plus 1s, and then I subtract 1. And this is where some more of our algebra skills come in handy, because we also need to know that 2 is the same as 2 to the 1 times 2 to the k plus 1, and then we have our minus 1. And when we have two expressions with the same base, we would add their exponents. So it becomes 2 to the 1 plus k plus 1, and then we have our minus 1 out here, so we get 2 to the k plus 2 minus 1. And we have to hope when we look at our right-hand side that we end up with this same expression. And the great thing is, absolutely, we will. So let's do that. So then the right-hand side of p of k plus 1 is, and we ended up with 2 to the k plus 1 plus 1, and then subtract 1. So we get 2 to the k plus 1 minus 1, which is 2 to the k plus 2 minus 1. We got to the same expression. So we would say, thus, the left-hand side of p of k plus 1 equals the right-hand side of p of k plus 1, and therefore p of k plus 1 is true. And I'll have to scroll up just a little bit so we can write our conclusion. So it follows, by mathematical induction, it takes a little longer to write that, it follows by mathematical induction that p of n is true for all n in the set of integers such that n is greater than or equal to 0. Such is the way of induction. For the last example from this section, we're going to use mathematical induction to prove that for every integer n that is greater than or equal to 1, we're back to our basis case being 1, that 1 times 2 plus 2 times 3 plus 3 times 4 plus the sum all the way up to n times n plus 1 is equal to n times n plus 1 times n plus 2 all over 3. And I'm hopeful that you will find the algebra on this one a lot simpler than the last one that had a big fraction. But only time will tell. So let's start with our statement. So let's let p of n be the statement, and let's rewrite our statement. 1 times 2 plus 2 times 3 plus 3 times 4 plus all the way out to n times n plus 1 equals n times n plus 1 times n plus 2 all over 3 for all n in the set of positive integers. We're back to our basis case, being that we should show that p of 1 is true. Then we know that p of 1 is, well, we get 1 times 2, and on the right-hand side we would get 1 times 1 plus 1 times 1 plus 2, and divide it all by 3. And 1 times 2 equals 2, and 1 times 1 plus 1 times 1 plus 2, oops, I made a typo there, 1 plus 2, all over 3 equals 1 times 2 times 3 all over 3, which equals 6 over 3, which also equals 2. So thus, the left-hand side of p of 1 equals the right-hand side of p of 1, and therefore p of 1 is true. Our induction is going to start just like all other inductions have. We're going to have to show that if we suppose that p of k is true, then p of k plus 1 is also true. So we need to show that for all n, oops, not n, sorry, for all k in the set of positive integers, if p of k is true, then p of k plus 1 is true. So we would say then, suppose that k is in the set of positive integers such that p of k is true. And again, you can change that such that to an and, if you like. So then we know that p of k is, well, we would have 1 times 2 plus 2 times 3 plus 3 times 4, right? Plus our sum all the way up to k times k plus 1 is now equal to k times k plus 1 times k plus 2 all over 3. And then we want to show that p of k plus 1 is true. Then we have that p of k plus 1 is 1 times 2 plus 2 times 3 plus 3 times 4 plus our sum all the way up to, and now anywhere we have an n, we're going to change it to k plus 1. So we'd have k plus 1 times k plus 1 plus 1, and it's going to equal k plus 1, k plus 1 plus 1, and we're going to write a lot of k plus 1s. K plus 1 plus 2 all over 3. And we want to start with our left-hand side, and then we'll show that it equals our right-hand side, just as we have on all the other ones. So then, the left-hand side of p of k plus 1 is 1 times 2 plus 2 times 3 plus 3 times 4 plus all the way up to k plus 1 times k plus 1 plus 1. Which we can say then, we also know that the first k terms are 1 times 2 plus 2 times 3 plus 3 times 4 plus all the way up to k times k plus 1. And then we added on that k plus 1 term, which is k plus 1 times k plus 1 plus 1. And we also know from our previous definition that we added up there, our supposition for p of k being true, that we know that the sum of the first k terms, right, is also the same as k times k plus 1 times k plus 2 all over 3. And so I can't quite align my equal signs the way I'd like to because there's a whole lot of algebra involved here. So I'm going to move it over just a little bit, but we can write this as k times k plus 1 times k plus 2 all over 3 plus our k plus 1 times k plus 1 plus 1. In other words, we end up with k times k plus 1 times k plus 2 all over 3 plus k plus 1 times k plus 2. And we know from previous experience that we're going to multiply the second half of our expression there by a 3 over 3 so that we can put it all over the same denominator. So we end up with k times k plus 1 times k plus 2 plus, and this is where we multiply it by 3 over 3. We get 3 times k plus 1 times k plus 2, and now we are all over 3. So when we start to simplify here, something sort of fun happens. Both terms have a k plus 1 and a k plus 2, so we can factor out a k plus 1 and a k plus 2, and in each case, then all I'm left with is k and plus 3. And this is all over 3. And I'm hopeful that you'll see that this is the right-hand side of p of k plus 1. But we're going to show it too, because that's what we're tasked to do with the proof. So we would say, then the right-hand side of p of k plus 1 is, and that was where we got k plus 1 times k plus 1 plus 1 times k plus 1 plus 2, all over 3. And when we simplify, we get k plus 1 times k plus 2 times k plus 3 all over 3. So thus, the left-hand side of p of k plus 1 equals the right-hand side of p of k plus 1. Therefore, p of k plus 1 is true. And we would say then for our final conclusion, it follows by mathematical induction. There we go, by mathematical induction, that p of n is true for all n in a set of positive integers, and we are finished.